All right. Good morning, everybody, or good afternoon, depending on where you are. I want to thank our speakers for coming today because this event was inspired by conversations that we had at the kickoff event, and so was organized post hoc. So I have to extend a special thank you to the speakers for being willing to talk to us on kind of a last minute notice. So what are we going to talk about today? The goal of today is to talk about teaching population biology. So this strategies for teaching topics between math and biology. And I think we have four amazing speakers to talk to us today. And the point of these talks is to inspire discussion. So if you have thoughts or comments, please feel free to add them to the chat, or even more preferred, raise your hand, and then we'll call on you and you can unmute and talk out loud. And this is the one time that is okay to have more of a comment than a question, because the whole idea is to curate these discussions, and we can continue this discussion after the talks in the coffee social on GatherTown. The address is here, it's in the email, and I will reshare that link at the end of these discussions. So I know that there's a lot that people have to say to us today, so I'm going to shut up and let other people talk. So the first person who is going to share with us is Clooney Pennings from San Francisco State University.
Thank you, Eileen. Sorry. And thanks everyone for being here. I'm honored to be speaking here alongside some amazing colleagues. And I'm going to try to share my screen. I made some slides. So I should start by saying that I've taken the liberty to talk about something slightly different, because in my daily life, I actually don't teach population biology much. I teach a lot of quantitative and computational skills. And so that's what I'm going to focus on. And so for those of you who don't know me, I'm a population geneticist, like many people here, I think. You may know my name because of my work on soft sweeps that I did during my PhD, and also later with Joachim Hermansson from Vienna. I also worked on other topics such as sympatric speciation, drug resistance evolution, and mutation selection balance. If you're curious to read something that I did more recently than the soft sweeps work, I'm really proud of Feeder et al. Feeder is Alison Feeder, who's at UW. We had a lovely paper that has both modeling and data analysis in one paper in 2021 in eLife. So next to being a researcher, I do a lot of teaching. I'm at a primarily undergraduate institution, San Francisco State University. It's a large urban university. We have a lot of undergraduates, and then we have a master's program too. And so I teach undergraduate students and master's students. We do not have PhD students in our department. And I have taught a whole bunch of things. I've taught bioinformatics, so that's more focused on sequence analysis. I taught genetics. I taught biometry, which is like our intro statistics class for undergraduates. I teach advanced biometry, which is for graduate students. Intro to computer science for biology and chemistry students, exploratory data science, also for biology and chemistry students, coding community, which is for grad students to help them with their own research. And then I teach an intro to machine learning class. So all of it is sort of in the quantitative computational space more than population biology. So I had to think when Eileen invited me to give this talk, like what is my approach? You know, how do I teach these things? And I think I tried to come up with some of the things that I think that guide how I teach these classes. And the first thing that I wanted to share is that I think trying to make things easier than maybe you think is a good idea. So for example, I teach this machine learning class, which is like a whole semester, so 15 weeks, 3 hours a week class. And I'm curious to hear from you all, like, what do you think would be covered in a full semester machine learning class? So here I'm going to ask for some input to see what you all would have in mind. So you can please type something in the chat that you think should be covered in a machine learning class. Oh, good question. Helen asks, what does 3 units mean? It means 3 hours of lectures. So for us, that means it's like, I don't know, I would say it's a full class. It's the most typical class that we teach is 3 units. Okay, so let me read a little bit. I can already see that there's going to be very different approaches to teaching a class like this if you had to teach a class. So applications to genomics, type 1 and type 2 errors regarding classification, some theory, benefits of machine learning relative to traditional approaches, garbage in, garbage out. Let's see, when to use machine learning as opposed to classical statistics, basic math, linear algebra, calculus. And then Anna is saying, what is different from regressions? What can you learn after? Okay, cool. So, I mean, I think honestly, like if you're like assigned to teach a class like that, there's a lot of decisions to be made. What I did is I decided to focus on the simplest machine learning approaches. So I basically spend most of the semester on decision trees, random forests, and then a little bit about gradient boosted trees. That means that what I don't include is anything unsupervised learning or clustering, anything deep learning. I don't do support vector machines. I don't touch images. I don't do cross-validation. I don't do any math, well, hardly any math, no linear algebra, no backpropagation, no feature engineering, and no dimensionality reduction. But some of the things that you all mentioned will be covered. So, you know, just by working with decision trees, of course, we can talk about, you know, things like data wrangling, ethical considerations. Students practice a lot using Python. We talk about genetics, and we use genetic data, you know, different accuracy measures and what they mean, how this could be relevant for healthcare. Ethical considerations such as racism that can be built into algorithms. We do some data visualization. We have time for guest lectures, and we have a lot of time for discussions. And so I think, you know, you can make any decision for what would have to be included in a class like this. But I think for me, what I decided to do is to be very light on the actual like machine learning content so that we can do a lot of things around it. And to have people hopefully at the end of the semester like feel extremely comfortable with decision trees and how they can be used in different approaches, even if decision trees are not obviously state of the art. methods that are often being used. And one of the big reasons for doing this is that I want students to feel like this is relevant and this is fun, so that they'll come back for a second class. Okay, the students like this class. I always get good reviews. And here, for example, one person says, like, it's a class where you can be creative and you're thinking and learning without having a hard, strong pressure to perform that will cause stress. Well, that is exactly what I would like to aim for. Okay, the second thing that I try to do is try to make it as relevant as possible. I feel like there is so much to learn. I might as well start with what the students want. So if I teach, there's one class that I teach that mostly has zoology majors in it. And so we work on animal data. And so, bigger than fruit flies, we work on birds and mammals and the kind of things that the zoology majors want to look at. If I work with master students, I try to spend a lot of time getting them ready to analyze their own data, because that's what they are often most excited about. And for those students who want to get a job, we do machine learning. Even if they haven't taken traditional statistics, they haven't taken maybe even calculus, they haven't taken other stuff. If they are excited to learn machine learning, I'll give them machine learning. I try to make it relevant also, like, depending on what is happening in the world. And last semester, there was a lot of stuff happening at our university because we are, broke. And so they're cutting classes. And one of the things that was happening is that there was a lot of talk about classes being cut in science and engineering, in part because we have some people, including me, that are very vocal in our university. And so the students started to feel like things were worse in science and engineering than anywhere else. So I decided, like, let's analyze the data. And so we analyzed the data. And so this shows, like, what percentage of the classes was being cut. And we found out that science and engineering was not worst off. There were other departments, other colleges that were losing many more classes. And so, I tried to make sure that whatever what is in the students' minds, what they care about, let's try to put that in the class. Is more fun, and they're more likely to want to learn, R and statistics if it's about something that they care about. Okay, so then something that I do in all the classes, whether it's a quantitative class or not, is like have students work together, work in teams. I think one of the most important things that students can do is talk to each other about what they're learning. I think that really helps in their learning. And so the students tend to like that, especially if it's low stakes stuff. If they don't have to worry about a grade, they really like to work together. And then finally, I try to make sure that students know what they can do with what they're learning. And so, for example, I try to invite speakers who are just a little bit ahead of them. So, for example, this is like one of my former students, and at the time she was like an intern at Genentech, and she got that internship in part because of her computational skills. And so I talk about that in my classroom in the hope that that will, inspire and motivate some of the students because they know that this could be useful for them. So in summary, I try to do easy, I try to do relevant, I try to do collaborative, and I talk about futures and opportunities for all of the students. And I think it's working because the students often, ask if there's more of this type of class. I will share my slides because if you want to learn more, I published about this stuff, and I shared a lot of my materials that everybody can use if you're interested. And also here are the links to all the programs that we have at SF State that I'm involved in. And a lot of this work is supported by NSF, NIH, and Genentech, both the company and the foundation. And I must say, it's been much easier to get money for this kind of stuff than to get money for my population genetics research. So I don't know what that means, but we've had a lot of support for this kind of work. So thank you everyone for listening. I hope that I'm on time, Eileen.
This is perfect. Thank you. So I really hope that people have points to ask, and I'm sure I do, but if anybody else has a question to start with. Okay, so maybe just to get us started, I'll ask the question. So I love this, that you highlight previous students and these career paths, because this is something that's really hard to do and really important. But for me, it's really hard to imagine how to follow up with students, especially after they've left the university. So how do you do that?
That's a good question. So sometimes these are like my own students, and maybe we're still working, like they were in my lab and maybe we're still working on a project. In other cases, I use LinkedIn. I try to stay connected with students through LinkedIn, and then I try to keep up with them. And of course, it doesn't work for all the students. I don't like have a system for it, but if a student, especially if a student was like a TA or something like that, or somehow I know them a little bit better than the others, I try to keep track of what they do. And then, and as a one thing I try to do is, if I feel like a student is doing something exciting, I try to do a little interview with them and I post it on my blog, and then I can use that for different classes. So I don't have to, get the person in person in my classroom, right? If I have like a little, if I have a little story about them, I can reuse that in many classrooms, and I can use it as homework, or like a conversation starter at the beginning of class.
Thank you for sharing.
Thank you for your wonderful presentation. So I have a question though. I also agree that maybe being collaborative and mentioning about the future is good, but day-to-day work is like sometimes pretty different from like the prospects, right? So like, what if someone finds the future very intriguing, however, he or she doesn't really like the day-to-day work? Like, it's just my concern. Yeah, thank you.
Sorry, I'm not sure if I understand the question exactly. You mean?
I'm sorry. So I mean like, knowing the future is great. Maybe a lot of people will go to this field because of the bright future in their mind. But if you really do the work, what you work on is like the daily work, the day-to-day work, which may be pretty different from like envisioning the future.
Okay. Yeah, so you're asking sort of like, how can we give like a more sort of realistic
like for example, you find that application to genomics or so like can be very promising and or so, but like day to day you need to like program dealing with dirty data work and so on, which you may not like, yeah, that's my concern.
Yeah. Well, first of all, I'm guessing that most of my students, I'm in a biology department, so most of my students are not going to be computational people in their future professional life. And so it's okay if they learn something about genomics and something about machine learning, even if they are not very good programmers. For most of them, I think that will be enough. And then for the ones that are interested, I would hope that they maybe get involved in some research, or if they do an internship, or like they can taste a little bit of that day to day and then decide whether they want to move on. Like, I don't think anyone would take my class and decide on the spot that they're going to be a computational biologist, right? They would maybe decide, oh, it's fun enough, I'll take another class, or it's fun enough, I'll apply for a summer program. And then who knows, maybe they'll find out that it's not what they want, and that's okay too.
IT. Thank you. Yeah. Thank you.
We have a question from Philip. Which teaching strategies have you tried and ended up failing, if any?
Oh yeah, well, things fail. Things fail all the time. Let's see. I mean, actually, honestly, earlier this week, so I'm teaching a grad student class, and it's a small class. It's just 15 students, and I thought that we could do a lot of like sort of discussion based and like sort of unplanned exploration. And then earlier this week, I told my students like, oh, I have to give this talk. What do you think? What do you think is important for teaching this kind of class? And then several of the students were like, what is really important is that the professor is well prepared and that they're like well prepared slides and that we know exactly what we're going to do. I was like, okay, well, thank you. Clearly, what I was doing this semester was not what you were hoping for. So yeah, I feel like things fail all the time. And I guess what one should do, not just in preparation for a talk like this, is ask the students, regularly what works and what doesn't work, and then, change what you can't change.
I'm sure that there's lots of discussion to happen, but I want to keep moving on with these inspirational talks. So if you have thoughts for Plumi, even as Joanna and Anna discuss, please post those in the chat. And thank you, Anna and Joanna, for being here.
Okay, I'm going to lead in part because Anna's internet is a bit unreliable, but she may jump in. So we have everything, of course, depends on meeting the students where they are, and we have a very different audience. And so our different learning goals, whatever. So our course that Anna and I have been teaching together for many years now is designed to teach non-theoreticians to read a theory paper. So I think in all education, I am a great believer in backward design. Standard course planning is you sort of decide what you're going to cover, which I agree with Plony speaking against this huge covering. And then you sort of write the syllabus, write the lectures, whatever. And at the end of it, you write the exam. And in backward design, you do it the other way around. You figure out what you want them to get out of it. And then you basically write the exams before you develop what the learning activity is going to be. And it just requires clarity as to what it is you want the students to get out of it. So our particular course, our learning goals, we are aimed at PhD students in ecology and evolutionary biology. There are other people in our class. There are sometimes PhD students in math. There are sometimes undergraduates. There are, our class is open to others. But our learning goal is formulated around a PhD student who does not have a theory background. And we think that as a PhD student in EEB, it is essential that they can read a theory paper. And everything in our class, that is the number one goal. But a number two goal that I think has been a great passion for Anna and also me, is to really understand the scientific method better. And in particular, with respect to this class, the diverse roles that theory plays within that scientific method. And for that, we assign them the paper that Maria Savedio already presented in an earlier gathering. And that's very much behind what we're teaching. So we have our own slightly different version of that. We really focus on, this is a slide we return to throughout the class, of our version of the scientific method, with the art of science being to ask a good question, and there not being, any one way of going about that. An emphasis on hypotheses in the plural, that, we're believers in strong inference and that you need to be comparing multiple hypotheses to each other, and that those hypotheses must make discordant predictions so that the data is able to tell the difference between them. And, the idea that not every paper is doing this entire process, but that the process of science as a whole is formulating an answer. Well, the formulating being the less scientific part, if you like, but the answering being this highly the core of the scientific method. And then the question of where theory comes in, and the answer being all over the place. And in particular, as per Maria Servedio's paper in Ecology and Evolutionary Biology, the role of theory is often quite different to in other fields. And in particular, in physics, often the hypotheses are expressed in mathematical language, and their purpose is to derive the testable predictions that will distinguish among the hypotheses. Whereas in biology, you will often have proof of principle or disproof of principle, essentially taking a verbal hypothesis and saying that it's not good enough to even be a verbal hypothesis because it failed some internal consistency check, or saying that actually there's this answer to this question that nobody suggested before, and that it should be placed on the table, that you thought the only hypothesis to explain for this question, to answer this question, was this, but here we show there's another one, and that these are where most things go. We then say that a lot of the time modelers in practice are doing number 1 and 2. They're coming up with weird and wonderful models that they're exploring, and in the process of exploring, they're coming up with questions they didn't think to ask, and they're coming up with answers that they didn't think of, that the model is leading them towards, but that more often that's not how the paper is written. The paper is going to be written as number 3 or 4. And then we distinguish these from statistical models, which are obviously extraordinarily important, but that we just sort of bracket as being outside the scope of the learning objectives of our class, and that we recommend all students take other classes that are focused on the use of statistics, but that's not what we're doing. And I'll just pause, Yes.
So I just want to add, Joanna's sort of saying this, but given the discussion on the last talk about meeting students where they are, I thought I would underline this. So I really think the students, the population that we have, these are biologists. Biologists often go into biology because they're sort of interested in science, but afraid of math and want to avoid math. And we end up having a population of students who often successfully avoided math, essentially for years. And so, Plony is nodding. So I think this is common in biology. And these are all our program is very selective. These are all very smart people, but they often have successfully sort of skipped all the equations and sort of given up on really trying to understand what models or theory papers are actually doing. And so this is, we ultimately think that cannot be successful in the long term, even if it is successful for an individual. As a field, we think it's incredibly important that biologists do actually understand what theory papers are saying. So this is just to motivate a little bit more the learning goal. And I think as far as the scientific method goes, it really is the case that everybody's heard of what it is. Our experience, I think, is that at the beginning of the class, people in a PhD program have at most a 50% chance of being able to accurately describe even just the core of what the scientific method is. So the core of the scientific method being, in my opinion, the fact that you generate at least 2 alternative hypotheses which are tested by comparing the predictions they make about empirical data. So the fact that these predictions are not what you think will actually happen, but are contradictory consequences of 2 opposing hypotheses, that core of this slide, in our experience, a lot of students either don't know it or are very unpracticed with thinking about it. And so we do think, even outside of theory itself, that it's incredibly important that we actually remind them of what this is. And as far as teaching strategy goes, I think Plony sort of said this implicitly, but in my view, it's incredibly important to understand where the students actually are by actually making them answer the questions you want them to answer, right? So just saying, oh, have you heard this before? Or do you know this already? Does not work. You have to force them to actually say to you, how does the scientific method in fact work? And then from their answer, you can tell whether they do or don't understand it, or what parts they understand that are important to you. So to me, one of the main effects of doing this active learning or working in teams or having the students do their own work is just to actually make it more transparent to the instructor where the students are, in fact, are. Because the students, at least by the time we get them when they're in a PhD program, they're incredibly good at pretending that they know everything. Like, they're very good at just kind of playing, you know, just nodding or saying things that sort of make sense on the surface about things, and just pretending that they are already professional and experts, when in fact they don't really know how this thing works. Sorry, Joanna, if you go to the next slide just real quick. And so this is this one. So this difference between proving a principle and deriving predictions, which is sort of one big core learning goal in our class for them to be able to understand what those two things are. Most students need several classes of practice to actually even be able to tell the difference between, sort of without any empirical data showing that a verbal hypothesis makes any sense or doesn't make sense, and connecting, you know, using predictions to actually compare to empirical data. And in part, I think that's because the word predictions gets widely misused. But so this is just echoing what Pluni said. This seems maybe a very small and simple point. It's just one categorical distinction. But we actually spend, I would say, I mean, throughout the semester, it comes up over and over again. We really need repetition for them to really get it. That's it. Thank you.
And I'll just add, you know, that's talking about what learning goals we have and how passionate we are about it. And I think what's really important in there is improving, you know, teaching them a bunch of math is not a core learning goal of the class. It is an incidental thing that may happen, but essentially within the scope of our one semester, we're trying to use whatever math they have, build only very modestly on it, and get them to apply it to sort of skip the equations, understand the assumptions, and understand the conclusions and read a theory paper. So this scientific method and this ability to read a paper, they're our goals. Fixing their math is not our goal, because that's way outside the scope of our one semester. And also the class wouldn't work, because while most of our students, like Anna said, their math is weaker than you think, pretty much every class we have at least one math student in there. And the surprising thing is that our class works anyway, even though we've got the most discordant mathematical, you know, we've got PhD students in math and people who've taken no more than 1 or 2 calculus classes. And yet the same, because that's not our learning goals, the same instructions ends up working for both. So yeah, backward design. If we want them to read a theory paper, then our assessment is that at the end of the semester, they're going to be told to read a theory paper and answer questions about it. And then you plan what you're going to do. And throughout the semester, they're going to be reading theory papers and answering questions about it. This is sort of core backward design, class design here. And then we are going to teach math. It's only going to be the absolute needed math, and it's going to be done in a just-in-time fashion in order to follow the theory papers that we're reading. And then we ended up finding that for them to really demystify the models, it's a good idea for them to reproduce parts of them. And we teach them Mathematica for that purpose. And so they, you know, Mathematica is quite useful for getting them to skip some of the mechanics of the math and really focus on what the mathematical objects are and how they relate to each other within the model. So those are sort of things that we end up doing on top of reading theory papers, because we've found that they can be good support to the core experience of reading the papers. So then which papers is then going to really control the course? You know, obviously we prefer the papers to be seminal. It's really interesting that, you know, what we're interested in really is really papers that illustrate the scientific method and illustrate the process of modeling. There are also a lot of theory papers out there that really develop, you know, here are the various theories of coexistence within ecology or whatever. And we find that when we asked our colleagues, they tend to nominate the second kind of paper, but those papers are really more of interest to people who are working on that particular question. And so, you know, we really focus on papers that have a stronger influence on the modeling side. Obviously, given our learning goals, even though proof of principle is the most common kind of paper, we have to sort of select non-randomly so that we get a diversity of roles within the scientific method. And, you know, we want to cover as many topics within ecology and evolutionary biology as possible so that students, you know, get at least one paper that's closer to their research interests. And then we want to cover diversity of modeling as well so that they get exposed to a variety of approaches, including, you know, sophisticated stochastic processes that's way above what you'd think their mathematical ability could be, because we don't want them to, you know, to only pick the easy math. Our skill is, how do you read a paper even when the math is too hard for you? And so it's important that we also pick papers where the math is too hard for them and talk at a high level about what that math is about. And so I thought it would be useful to show, sort of, in teaching this many years, we often kind of kicked one paper out and tried adding a new paper until we got the balance we like. For several years, we've kind of settled on this. This is my final slide. So I can walk through it. I mean, actually, there's one I want to pay attention to, which is Hardy 1908, because they've all learned Hardy, except maybe math students. All the biology students in the class have learned Hardy-Weinberg equilibrium in the classroom, and what they have learned is all wrong. And when they read Hardy 1908, they'll find something else. So they've been taught in the classroom that how to do some statistical test for whether you get the ratio p squared 2pq or q squared. And then when they read the paper, they find it has absolutely nothing to do with that. He is disproving the verbal hypothesis that dominant alleles will tend to rise in frequency until they reach a frequency of 3/4. And, you know, some profound confusion between selection and dominance that was present in the community at the time. And so, you know, they get to see, you know, this sort of shocks them into the role of theory in the scientific method. So it also reinforces correct understanding of Hardy-Weinberg for the TA roles that many of them have, but it also shocks them into people, the idea that the role of theory is to generate predictions has led to textbook material completely historically misrepresenting why a particular model was historically important. So I think I wanted to sort of mention that one in particular. Anna, are there any others you wanted to highlight?
I mean, I don't know if I want to highlight any particular paper. Different people in the audience now may recognize, you know, Luria and Delbruck or something like that, or Hubble. But it really, Joanna said this, but just to emphasize, yeah, we love it if there's a seminal paper, because then there's a side effect that they've heard of this paper before. But we really emphasize a diversity in approaches in modeling or theory here. So the lists, you know, used to contain other papers at one point, and then we slowly swapped things to kind of optimize the diversity along all three of those columns that you see. And so it's important, I think, for the students particularly to see that the role of models, like Joanna said, is usually not to make predictions. And I also want to maybe point a finger at the forecasting thing. So models, in our view, right, sometimes but rarely are meant to make predictions that will empirically be tested. For example, the Luria and Delbruck paper famously made different predictions about, so, you know, it was concerned with basically whether mutations happen independently of the need to evolve or happen in response to bacteria needing a new trait. And so those two hypotheses, whether the mutations are independent or dependent on need, those two hypotheses made two different predictions about what you should see in empirical data. And that process of making predictions was, in this case, a mathematical process, right? That is the function of the model in this paper. But overall, you can see that that's pretty rare. So models often don't do that. But the Stainforth paper is a climate, you know, it's a climate science paper. It's about estimating what the climate will be under different circumstances. And so we call that forecasting, because in that case, the purpose of making a prediction, in a sense, is not the prediction in the scientific method sense. It's actually estimating what the climate actually will be a certain number of years in the future. So this is kind of an applied purpose. In a sense, it's not science at all, because it's not trying to test any hypotheses. It's not trying to generate new conceptual knowledge. What it's trying to generate is an applied, useful number, which is, what is the climate going to be under these different, maybe, interventions or circumstances. So we call that forecasting, in order for the students to see a clear difference between, I want to actually estimate how warm it's going to be 50 years from now, and I'm generating two opposite predictions about what my empirical results will be in order to test the hypothesis. So we feel that emphasizing that difference is important. And by the way, Martinez was at University of Arizona, which is why we picked the paper, but I think he is at,
He was at
also
San
at
Francisco
Stanford.
State first, yes. Okay, so we've got to move on. I actually forgot I had one more slide, but very briefly, we also, you know, play with having them classified. These are not perfect classifications, but you know, this is sort of another of the tools we use for them to think about how different models are different, and we go through some of this process to get them to kind of think at a high level about the models rather than sort of focusing on getting from one equation to the next. Okay, we are over time. Sorry, guys.
So clearly we picked some good universities to highlight here. Is there a quick question or thought for Joanna and Anna before we move on to our last topic? Yes, Nicole.
Yeah, thanks. I really enjoyed that. It's more of a comment than a question, but Aline said that was fine. Anna, so first of all, I really liked the framing. I think this is super cool. Love the framing. Anna, I think, made the point that in biology, we seem to have a lot of PhD students who have managed to avoid theory or math. But something happens when they get to grad school, and like some of them like either want to understand it or retroactively appreciate its value and like kind of want to do it. And I guess if I was going to make this a question, it would be like, why are the people in your class? Like you mentioned that as a field, this is something we should want, but grad students don't necessarily do things to help us like improve the fields. Like, why do you think they're taking this class?
So I'd say Anna and I would like to make the class compulsory. We haven't yet succeeded. Frequently, the students who do take the class end up coming round to thinking it's compulsory, but I think it would be not unfair to say that Anna and I have at various points pushed some of those students into being into our class, either from our own labs or being on their committees or whatever. But I mean, others just know that they need to read, you know, if they're more mature, at some point it's, you know, they realize, shit, I don't understand enough math. I can't read this theory paper, but I have to read these papers because everyone cites them and they're really important to my work. And so one hopes that they come to it from that. I think we'd prefer a system where it was made part of the core curriculum for the PhD program, because it just, I think we can, you know, I think empiricists should be able to agree that at a comprehension level, it's an essential, it's not an optional. And to be very clear, some students might be inspired after our class to go and learn more math, but that is not our learning objective. That is a side thing.
Awesome, thank you.
So I'm sure we all have lots of thoughts and questions, so please save those for the coffee hour. More incentive to come and join us for the coffee hour. Troy, thank you for being here.
Okay, everybody can see that? All right, so I'm going to focus maybe a little bit in a different area. I want to talk a bit about some of the experiences I've had in trying to teach mathematics to people who are interested in life science in some way at the undergraduate level. I want to focus solely on the undergraduate level here. I want to highlight a couple of things that have already come up in some of the other talks as we go along, because I think there's some really great ideas that have been talked about so far. So I like to start with a slide like this, which to me kind of illustrates part of the problem of teaching math to anyone, really. People tend, on average, to not like math. So people hate math, 4 out of 10 people hate math, for example, right? And there's obviously some great irony in that particular article. And it's already been said, people people who go into the life sciences are people who are interested in science, but they're trying to avoid math. And what I want to talk about is a couple of different things I've been involved with that address this problem. So one of them you might think of is, how do you reach those students who went into the life sciences to avoid math and are now coming back because they're interested or realize they need to learn some math? And so I think some of what's been talked about today is related to that. And I certainly have a lot of interest in that. But I'm going to put that aside, and I want to look at the second one, which is, what can we do in terms of teaching math at the undergraduate level that will encourage students never to leave math? And I don't mean they should become math majors, but I mean they should be happy enough with math that when they go into a life science degree, they may still take other math courses because they both enjoy it and think it might be useful. And so that's where I want to focus my presentation on. So I'm going to talk about 4 things. I want to talk about kind of types of courses, which I'll call terminal courses versus introductory courses. So I'll talk about the structure of courses that are aimed at teaching math to life science students, and a bit of a comment on what it means to be rigorous in these courses. And I'll finish with an example of how I've been trying to do these things in a calculus class that I've been teaching. So I guess the first thing that I think is important is, if you ask people in biology departments what should be in the first year math course for them, you'll often get a list of things. And here's a list, and usually things like calculus are not actually at the top of the list. It's usually stats of some form, probability, often linear algebra now more than calculus. If you ask mathematicians this same question, they don't really focus on the techniques or the topics like this, but rather the way of thinking that underlies them. And so that's sort of the approach I want to take here. And it's maybe going to be a little bit of a controversial approach, I hope, in that I'm going to argue that we really need to focus on the math while doing it in the context of important and genuine applications. But the presenting things along the lines of the structure of the mathematical arguments is a good thing to do, because it helps people to learn how to think mathematically, in a sense. And by that, I mean basically in a deductive sort of way. And so I want to, rather than focus on techniques and tools, I want to focus on using those tools as a way to develop a way of thinking. And part of the reason for this is, I think you could debate what the right list of techniques and topics is, but reality is, first, I think almost any topic you think of has been used in some context in the life sciences to do something interesting and useful. So you can always find examples. But I also think that it's better to develop the ideas behind them rather than the topics themselves, because the reality is also that students are not going to remember whatever the techniques are that you teach them anyhow. So they're going to have to come up, when they're faced with needing these, they're going to need to refresh their memories at very least in order to use any of this. And so I think it's more useful to focus on the underlying structure of the ideas. Now that brings me to this notion of course structure. So if you look at the way people try to design first-year calculus classes for life science students, there are kind of 2 broad ways they do it. One of them is they focus on modeling, basically. And the other is they focus on the math and use modeling or applications in that to demonstrate how that math might be useful. And I'm going to argue that it's the second approach here that's the right one to do for introductory classes. Modeling, I would say, is the right thing to do for upper year classes when you're trying to bring people back into math that might have left early on. But if you're trying to encourage people to stay in math and to develop sort of mathematical fluency, I'd argue that the mathematical structure of the course is actually an important part of that. And so, of course, to make students believe that it's useful for their degree in life science, you need to do that in a way that still highlights genuine applications. And so, but my example at the end, I'm going to give to try and convince you that it's at least plausible that you can do this. You can develop a course that's structured based on the mathematical structure of the subject, but you can provide genuine, relevant examples that are of interest to life science students. Another thing I think is worth talking about is rigor. And I bring this up just because, often people talk about, you're using a model because you want to be rigorous in your thinking and this sort of idea. And I think that people often, and particularly actually, I think mathematicians often conflate the notion of rigor with abstraction. So abstraction, I think, can be very hard. It can take a lot of work to abstract ideas in a way because it's difficult to do that when you're starting to think in a very abstract context. But being rigorous is actually not hard. To my mind, rigorous means basically not leaving anything to a leap of faith or someone's insight. You have to justify everything you do. And in a sense, that makes things much simpler. There's never a point in time where you're appealing to someone's intuition to make the next step. You're justifying it in every step of the way. And in a sense, to me, that's why modeling is not the right thing to do at the introductory level, because modeling is often hard in that if you look at papers where people have built models, they do this all the time, right? They make leaps, not leaps of faith, but leaps that are based on intuition and things. And students often come away wondering, how would I ever have been able to do that? Because, I wouldn't have seen the problem in that way to be able to use that trick. And to me, then, to be rigorous in a course like this is to be completely unambiguous about every step you take along the way so that anybody who's willing to follow along can follow it. And so it's what I'd call readable rigor in a sense, rather than abstraction. So I'm going to finish with just an example of how I've tried to do this. And it's an example that is involving vaccination and pathogen evolution. So I won't spend a lot of time explaining the example, but this is what I call a case study that kind of sits on top of an entire calculus course that I teach in first year. And what I do is give them an introduction to, vaccines, how vaccines work, and then the idea that maybe vaccines can drive the evolution of pathogens, because some vaccines that are perfect these vaccines are perfect. They prevent infection by all these different genotypes, for example. Some are kind of act like sieves, like HPV vaccine and influenza, where some things are prevented and others aren't. And you can clearly see why that would select for a different distribution of genotypes afterwards. And others are sort of more in between, kind of leaky in some sense. And so I show them data from an experiment that tests these ideas of whether or not vaccines can drive the evolution of disease severity, in this case, in mice. And I get them to try and explore the data and understand the data and what it says and get a real feel for what the experiment is showing. And then pose these two questions at the end that we're going to use our mathematical techniques that we develop over the course of the year in this calculus class to answer these. So can we understand why this outcome in this experiment is the way it was? Why did it drive the evolution of disease severity in the way it did? And given we have an understanding of that from our mathematical modeling, can we design vaccines that wouldn't have given rise to evolution, vaccines that are evolution proof in some way? And so the idea is, as I said, this is a standard kind of calculus class. So here's a list of, basically the topics that we cover in a standard kind of order, building them up in a mathematical context: functions, limits, derivatives, integration, differential equations, and a bit of stats at the end. And the idea is, as we develop these topics, again, from a mathematical perspective, so everybody sees the sort of logical structure of the subject being built up, we go off on asides and we show how what we've learned about functions and transformations of functions and limits of functions can be used to understand parts of this problem. And so we first understand things like the relationship between transmission and parasitemia within a mouse. We eventually get to a point where we build an optimization model that we use to predict the level of disease severity in each of those. And you can make predictions that are qualitative relative to one another without knowing anything about the specific parameter values of the model, well, knowing virtually nothing about them. And then as we get into some of the ideas of statistics, we can then start to nail down in a more quantitative way the kinds of predictions you might make from a model like this, and then compare those predictions to the data and see where, sometimes they fit really well and sometimes there's pretty big discrepancies. And so that points to this sort of iterative process of modeling as well, where there's clearly something missing in our argument so it doesn't capture all of the patterns in the data, but it does capture in some important sense some of the qualitative features. But again, all of this is built, the course is built from a mathematical perspective. to illustrate the sort of logical structure of the discipline and the way that mathematical arguments are made. And then we sort of lay this whole case study that runs over the course of the year on top of that course. So I'm just going to finish with this summary slide. And so again, I focused only on the early part of an undergraduate education, sort of introductory courses. I think in my mind, the kinds of things you want to do for upper year courses for students who are coming back to math can be quite different. And I think it's important to distinguish between modeling and math as well. And I lean more towards emphasizing the math on these introductory courses and more towards emphasizing the modeling in the upper year classes. And maybe I'll leave it there. I'd rather have questions and have discussion than say any more.
Wow, so much fun. So many different focuses. So thank you for that. Are there any particular questions that we have right now? Nicole, thank you.
I'm gonna implicate my buddy Anil here. I don't know if you can also see him.
Hey, Anil.
He had a question, but apparently I'm speaking for him. His question was, do you have any evidence that this translates into students like not leaving math?
The short answer is no. I would say no systematic evidence. You know, it's always a bit hard and difficult to rely on anecdotes. So the answer is no. Yeah, I guess only anecdotally where I've heard students, you know, say things like, this is kind of piqued my interest in math. I guess maybe I'm kind of waffling. Maybe the one thing I will say, though, is I've tried to do this previously in other courses that didn't focus as much on the math, that were a little bit less math heavy and more modeling heavy. And it got people inspired to go into math. But then when they went into the second year math courses, they were often not prepared for what it was. They didn't realize what math actually was. It wasn't the sort of modeling that was being done in this first year course. And so it was a bit of a rude awakening. So I guess that's not evidence that this works, but in some way I think of it as evidence that, you know, if I did the modeling approach, it almost falsely advertises what going into math is about. I don't know if that gets anywhere near what you were thinking of, though, Anil.
I think you answered my question.
And I think it's cool.
I actually really want to continue talking about that in the GatherTown. But Joanna, do you have a quick question? And then we'll transition to GatherTown to have a bigger discussion.
Sure. Basically, a kind of follow-up to some degree. What's sort of the politics of what the students must have in order to progress? You know, this comes into, you know, whether they're prepared for the next math class, whether there's a path for them, and also MCAT requires this, you know, do you get a lot of pushback that, you know, you haven't provided the coverage or the preparation needed? And I should just say, I love what you're doing. I mean, it sounds really good, but, you know, are there sort of political curriculum things you need to navigate, and how have you managed that?
Yeah, there are, and it's difficult. That's sort of, I didn't spend a lot of time talking about it, but it's kind of what I meant by terminal versus introductory courses. So right now I'm also teaching an introductory calculus class for a direct entry life science program. And it's truly a terminal class. They're not going to take anything after this. They don't have room to take anything else in their degree because of the way their degree program is structured. And so for a course like that, I was much more free to design it in any way I wanted because I didn't have to have certain prerequisites covered. But for the more mainstream calculus for life sci, where students could go anywhere afterwards, you're absolutely right. It's a fine line between, you know, covering everything because you have to cover it and not. And I prefer to cover less but focus more on the ideas rather than trying to cover a lot and just give them the techniques.
So obviously lots and lots more to talk about. I'm going to share my screen quick in case anybody needs the link to the GatherTown, which I've also put in the chat. So I will see you there in a few minutes.
All right.
Thank you, everybody, for talking and your wonderful questions.